this semester with DAM's on. DAM doesn't really need that much of an introduction, but I'll give a very brief one. I think he got his degree in Moscow, working with Rubikov. He came to the US as a postdoc in Seattle, which is where I met him, moved on to be a postdoc at MIT. He was then a faculty member first at Columbia, then at the INT, and for the past 10 years or so as a university professor at the University of Chicago. He's obviously known for many, many things, for kind of non-equilibrium behavior in field theories, thermalization, fluid dynamics, ADS-CFT correspondence, pointing out the importance of eta over S and possible balance on eta over S. And has done a lot of beautiful work on kind of symmetries in effective field theories for either condensed matter systems or other many-body systems in general. And I think that's what he'll talk about today. So we're very pleased to have you. And as Uli already mentioned, typically the way we do this is that I'll try to monitor the chat. If I see any really urgent questions, I may interrupt you, but I think we'll try to just have to talk and do questions afterwards. Well, thank you very much.
Okay. Thank you very much, Thomas, for the introduction. And I would like to thank the organizer for inviting me to this series of seminars. So I'm going to tell you about some new facts, I think, that we found in very low energy nuclear physics. So this, I have to apologize, this doesn't really directly related to the RIG program, at least right now, but maybe in the future it may find some application there. So the talk that this talk is going to be based on a paper, mostly on the paper that Hans Hammer and I wrote last year, and there is a very nice introduction to the physics that we are concerned about in the in this article by Thomas and Gordon Bain that I enjoyed reading. They put our work in a much larger context of different kind of physics. So let's first talk about the role of symmetries in physics. Obviously, we know that symmetry have been playing a very important role in many subfields of physics. In elementary particle physics, space-time symmetry is the key to understanding elementary particles. So in particle physics, we have Lorentz and Poincaré symmetry, and the representation of Lorentz and Poincaré symmetry determines the properties of elementary particles. Another symmetry, larger group of symmetry called conformal symmetry, is also important in quantum field theory, also in the theory of second-order phase transitions. The Poincaré symmetry is a symmetry of Minkowski space-time. It consists of time and spatial translation, rotations, Lorentz boost, and the elementary particles can be classified as using the representation theory of the Poincaré symmetry. This representation classified by the mass and the spin of the particle when the mass of the particle is non-zero, and when the mass of the particle is zero. Just from the property of the Poincaré group, we know that the particle have helicity instead of spin. The conformal symmetry is a larger group, larger than the Poincaré group. These can be thought of as transformations of space-time that preserve the angle. So here I'm trying to imagine a space-time. In this case, I try to image it as a two-dimensional space. Poincaré transformation would preserve both length and angles, but conformal transformation preserve only the angle. So if something has a two line intersect at the right angle here, after the transformation, they would intersect at the same right angle. However, the distance may change under the conformal transformation. For example, the group of conformal symmetry include dilatation, where we take a coordinate and change all the coordinate by the same factor lambda, and obviously then the distance, all distances will also be multiplied by the same lambda. In addition to dilatation, the conformal symmetry group also contains more sophisticated, harder to imagine transformations called proper conformal transformations. Quantum field theory with these conformal symmetries are called conformal field theory, and they have interesting applications in theoretical physics, including in the theory of second-order phase transitions. One can ask the following question: whether this conformal symmetry is a symmetry in particle physics, like the symmetry of the standard model, and one can conclude right away that this is not a symmetry in the standard model by using a very simple argument. Consider a particle with mass m. Its energy depends on the momentum as E equals square root of p squared plus m squared. Now, we have said that conformal symmetry include dilatations. Under dilatation, both energy and momentum are multiplied by the same factor lambda. And if we look at this equation, we see that this equation cannot be preserved if the mass of the particle is non-zero. In the standard model, a lot of particles have non-zero masses, and so the standard model is not a conformal field theory. A field theory can be conformal only if it contains only massless particles. Conformal field theory can also be interacting, and in this case, one doesn't have particles. We have some fuzzy stuff that are not usual particle in the sense that they are not poles in the correlation in the Green function. So in 2007, Howard Georgite wrote a relatively speculative article where he speculated that the notion that he called unparticle may be relevant in particle physics. So we can approach Georgite's unparticle from the side of conformal field theory. Suppose we have a conformal field theory with some operator with dimension delta. The two-point function of this operator scales like 1 over x to the power of 2 delta. It has to be scale invariant. So this is the only form that it can have. In momentum space, the Fourier transform of this function is power of the momentum. If the dimension of the operator is 1, then the propagator is the same as the propagator of a free particle. Free particle has dimension 1, of course. But if the dimension of this of the operator is a general number, not 1, then the propagator in general would have cuts, not poles. They have cuts that goes right from 0 to infinity. And that means that this object U, operator U, doesn't create a particle, but it creates some kind of excitation whose energy is not fixed even when the momentum, total momentum, is fixed. Georgite called this object an unparticle and hypothesized that it can be a hidden sector coupled to the standard model. That, in a more theoretical language, his hypothesis is that the standard model is coupled to a certain interacting conformal field theory. So if that is the case, then we can hope to see these unparticle in the reaction involving usual standard model particles. For example, we can take two particles, A1 and A2, collide them together, and let's imagine that it becomes one particle B and another an object that is an unparticle U. So this object U is some kind of a fuzzy object whose energy is not fixed when the momentum of U is fixed. So if that is the case, we know that the energy momentum conservation does not fix the total, it does not fix the energy spectrum of final particles. Unlike the case when both U and B's are usual particles, the energy spectrum of B is now continuous. One can do calculation using the rule of conformal field theory and show that if we plot the differential cross-section, the sigma over, say, the invariant mass of this U object, we find that this would be something that that has a power law threshold behavior when this invariant mass is 0. So that is the prediction of Georgi, that near the endpoint of the near the kinematic endpoint, the cross section of this process has certain power law behavior, and the power depends on the dimension of this operator U. Delta is equal to the dimension of the operator U. To summarize the experimental situation, I've just mentioned that people have tried to look for this unparticle, and the search, I think, so far implies a negative result. No unparticle has been found at the LHC. So let us now return to non-relativistic physics. In non-relativistic physics, we also have systems with scale invariance, similar to the scale invariance in relativistic physics. Schrödinger equation of a free particle, written here, implies that from one solution, we can get another solution by rescaling space and time by different rate. If we rescale time twice faster than space, then the Schrödinger equation, which is first order equation in time derivative and second order in space derivative, would be invariant under this transformation. And that property persists for system of not just one particle, but n particle. Non-interacting n particle system would also have the non-relativistic scale invariance. We can also write down theories of particles that interact with each other, but still have non-relativistic scale invariance. And one simple case is when we have interaction potential that is 1 over r squared. So when the interaction potential has dependence on the distance between particles, 1 over r squared, one can repeat the mathematical manipulation and check that the scale invariant is still valid in this case. A system of n particles interacting through a pairwise 1 over r squared potential is should be scale invariant. That is according to this simple argument. In fact, the symmetry of the free time-dependent Schrödinger equation and the Schrödinger equation with 1 over r squared potential is larger. One can check that if one take time t and then transform it to t over 1 plus alpha t and x to x divided by 1 plus alpha t, then the effect of these change on the Schrödinger equation can be compensated by supplying the wave function with a certain prefactor that is phase and the overall prefactor that keep the normalization of the wave function invariant. So it turned out then that the free Schrödinger equation or Schrödinger equation with 1 over r squared potential has a larger group of symmetry, and this group of symmetry is called the Schrödinger symmetry. So the Schrödinger symmetry consists of time spatial translation, the Galilean boost, scaling, t goes to lambda square t, x goes to lambda x, and one of these so-called proper conformal transformation that I've seen mentioned on the previous slide, and then also rotation. This group of symmetry is called the Schrödinger symmetry, and sometimes also called non-relativistic conformal symmetry, since it seems to be the largest group of symmetry that is available in non-relativistic physics. One can write down the Schrödinger algebra, the algebra of this transformation, in terms of the usual x and p variables in quantum mechanics. The total momentum is sum over PA, where I take the I take the sum over all particles. A is the index that numbers the particles. We can check the following operator form a closed algebra: total energy, H, total momentum. Galilean boost is just basically sum over the coordinates of the particle weighted by their mass. So it's basically the position of the center of mass. Dilatation operator is x dot p, something that's not very clear to have any meaning in classical physics. And then the proper conformal transformation simply is the sum of the coordinate square of the particle, or in some think about that as the moment of inertia of these particles. And then angular momentum and mass, these operators turn out to form a closed algebra, which using the usual commutation relation in quantum mechanics, we can construct a table how these operators commute with each other. So these operators turn out to form a closed algebra, the Schrödinger algebra. Okay, now we can ask the following questions. Is the Schrödinger symmetry good only for non-interacting theory, or theories with 1 over R square interactions? These theories are interesting. However, it's hard to, the non-interacting theory is rather trivial. 1 over R square interaction is rather hard to find in nature. The question one may ask is there a scale invariant system, or system with Schrödinger symmetry with a short range interaction that would be easier to imagine to be realized in nature? And the answer is yes, and that is the so-called unitarity regime. The unitarity regime, I think, was first noticed by Zeldovich in a paper that he wrote in 1960 or 1959 and published in 1960. And he was worrying about nuclei with large number of neutrons, and he made some predictions for the what we now know, what is now known as the Fermi gas, unitary Fermi gas. He called that Fermi gas with resonance interaction, which is basically unitary Fermi gas, and he made some prediction for the energy of such a gas, which is later became very important. Very important in physics. So the unitarity regimes can be imagined the following way. Let us take a system of 2 particles with interacting through, for definiteness, square wave potential, tuned in such a way that there is a bound state exactly at 0 energy. So the depth of the potential and the width of the potential and the size of the potential is such that there is exactly 1 bound state at 0 energy. And then we can imagine shrinking the size of the potential to 0, but keeping the depth such that there is always 1 bound state at 0 energy. That requires the depth to becomes the potential to become deeper and deeper when we shrink the size of the potential to 0 size. So that is the relationship between the width of the square wave potential and the depth, so that we have 1 energy bound state with 0 energy. Taking this system and take the limit R naught goes to 0, we go to the so-called unitarity regime in quantum mechanics, in which in which you can see none of the scale parameter remains. The binding energy is 0 and the size of the potential is 0. So the problem has no dimensionful parameter. So this is the regime where the scattering length is large. We know that when the scattering length is large and positive, then the potential has a shallow bound state with energy h bar square divided by ma square. When a goes to infinity, the scattering length, in the infinite scattering length limit, the binding energy goes to 0. This limit is called the unitarity limit, and this limit can be made rather formal, independent of the potential, as a statement on the boundary condition on the wave function. So the wave functions has to behave as c divided by the distance, some constant divided by the distance between these two particles, plus a regular part that vanishes when the two particles go to each other. So this function is special because the Laplacian of this function is 0, and it satisfies the Schrödinger equation near when these 2 points goes together. Okay, so the system with large scattering lengths exists in nature. There are a few of such systems seems to exist because nature, for some reason, the fine-tuning for us. If we take two helium-4 atoms, for example, they would form a bound state which has a size of about 100 angstrom. The scattering length between two helium-4 atoms is large and positive, and that corresponds to a molecule. There is a molecule, helium-2, which binding energy is of about 1 millikelvin. Temperature of that corresponds. The energy of the potential of interaction between two helium atoms is about few Kelvin. The binding energy is fine-tuned to a factor of 10 to minus 3. It seems to be an accidental fine-tuning in nature. An example closer to nuclear physics is the neutron. Two neutrons do not form a bound state, but the binding, they almost form a bound state. The scattering length between two neutrons is minus 20 Fermi. If one flip the sign of this A, that would correspond to a binding energy of about m, so ma squared with about 0.1 MeV, which is much smaller than the typical scale in nuclear physics. In low energy nuclear physics, one usually talk about the scale of a few MeV, which is the binding energy per particle in a nucleus. But this energy scale in the neutron sector seems to be much smaller. Neutrons, in the interaction between neutrons is also pretty fine-tuned. People can also make a system where the interaction, the scattering length can be tuned by hand using the magnetic field and a technique called Feshbach resonance in ultracold trap atoms. And in all these cases that we have listed here, the interaction is pretty short range. The range of interaction in helium or atom is about a few angstrom, in neutron a few Fermi, but the particle fields, if they have low energy, the particle fields the influence of each other at much larger distance. The distance of about a few hundred angstrom in helium and a few tens of Fermi in the case of neutrons. Okay, so in the case of unitarity fermions, we can formulate the problem formally in the following way. So let me define this problem can be defined in a way that does not require the specification of any limiting procedure with any potential. We just say that we have two types of particles, X and Y. Coordinates of spin up and spin down particles we denote as X and Y. there is n1 spin-up particles and n2 spin-down particle, and the Hamiltonian is an operator which is just the sum of the Laplacians of spin-up and spin-down particles. This seems to be just trivial quantum mechanics of free particle until we specify the Hilbert space. The Hilbert space of our problem is a non-trivial space of all wave functions psi of x and y. So by x, I mean the collection of xa, and by y, a collection of yb. And we say that whenever two particles with opposite spin approach each other, the wave function we have in such a way that it is a singular function proportional to the inverse of the distance between these two selected out particles, plus regular part that vanishes when the coordinate of these two particles approach each other. This turned out to be a well-defined mathematical problem, the problem of finding the eigenstate of this Hamiltonian on the glass of the wave function that we have this way. There are two interesting facts that one had to check. One is that the Hamiltonian is a Hermitian operator that can be shown that for the class of this wave function that we specify here, H is still a Hermitian operator with real eigenvalues. And second, these wave functions can be normalized. And together with the fermionic statistics, that is when two particles with the same spin are exchanged, the wave function changes sign, we have a well-defined mathematical problem with no free parameter. This is a problem of unitarity fermions, as one can formulate to mathematicians. The unitarity Fermi gas have interesting properties. If you have a large number of these particles in a finite volume, we can ask the question of, for example, thermodynamics of such a system. And it turned out the scale invariance is very useful properties that allows us to make statement. For example, a statement that can be made is that the ground state energy of a system of n particle, say equally divided between spin up and spin down fermions, depends on the density of this particle in the same way as a free Fermi gas, except for a new dimensionless parameter Xi, which is called the Birch parameter. The energy of such a gas is equal to Xi times the energy of a free Fermi gas with the same density. So the factor Xi has now been computed numerically and measured experimentally to be around 0.37. The energy this unitary Fermi gas have enough attraction between the particles to reduce the ground state energy by more than 60%. Okay, so one can formalize the many body physics of this unitary Fermi gas by using a concept called non-relativistic conformal field theory that is can be built up. A lot of statement about non-relativistic conformal field theory can be built up rather formally in analogy with what one does in relativistic conformal field theory. Many notions can be extended. For example, the notion of operator dimensions, operator state correspondence. For example, let me give you one example of what the notion of operator dimension is in the case of unitarity fermions. So let's do a little bit of field theory, non-relativistic field theory, and write down the field theory describing fermions interacting with the short-range potential. So here we have kinetic energy of the fermions, and here's the potential energy, which is just a delta function interaction with some strength C0 coupling constant. This theory can be rewritten by using an auxiliary field phi, which is going to be useful. We rewrite the 4-point interaction between the fermions as mediated by some object called phi. So this phi here doesn't enter the Lagrangian with the kinetic term. It's just an auxiliary field at this moment. But we can use the Feynman rule to compute the full propagator of phi. So the full propagator of phi turned out to be to have non-trivial behavior in as a function of momentum in space. So let me show you how to compute it. Phi, the full propagator of phi depends on the one loop graph that contribute to its self energy. So the inverse propagator of phi is the sum of the term that we have in the Lagrangian, this term, and the one loop graph that renormalizes the Green function. The one loop graph turned out to be linearly divergent, and so this diagram is equal to lambda, which is the momentum cutoff. And if we subtract this lambda, there is a finite part that is the square root of p squared minus omega. The unitarity limit can be interpreted in this field theory as a fine-tuning where these objects c minus 1, c naught minus 1 plus lambda is equal to 0. In general, this sum is the scattering length. When the scattering length, inverse scattering length, when the scattering length goes to infinity, that is the fine-tuning in which this is 0, and the propagator of phi becomes well-defined finite function, non-trivial function of p and omega. Physically, we fine-tune the attractive short-range potential to have a bound state at threshold, and the presence of the bound state at threshold is the reason why the propagator of this object phi has a cut that stretch from 0 energy to infinity. So this propagator corresponds to an object which has dimension 2. In the field theory that we have written here, the dimension one can do dimensional counting and check that the dimension of the scalar of the elementary field psi to be 3/2. So it's momentum to the power of 3/2, while this operator phi has dimension 2 according to this propagator, which is not equal to the sum of the operator of psi and psi up and psi down. And that's the consequence of attraction between these two particles. The attraction between fermions lead to a modification of the dimension of the composite operator. Okay, now there is a statement that one can make and prove using the basically algebraic manipulation with the conformal algebra. We can show that the dimension of operator in here, so-called primary operator, dimension of certain class of operators can be put in correspondence with the energy of a state in a harmonic potential. So let me illustrate this in the case of unitarity fermion. The simplest operator in our field theory is the operator that creates a single or annihilate a single particle, psi, which have spin either up and down. The dimension of that operator 3/2 correspond to the ground state of a single particle in a harmonic potential, three-dimensional harmonic potential. We know that if you put a particle in a harmonic potential, its energy, the ground state energy is 3/2 h bar omega. Omega is the energy, the frequency of this harmonic oscillator, and that corresponds to the dimension of the operator being equal to 3/2. Okay, now if we take two particles and put it in a harmonic potential, two fermions which spin up and spin down, then the following thing happens. If the two fermions do not interact with each other, we can put them in the same ground state, and the energy of that state would be equal to 3 times h bar omega. So in the free theory, the dimension of the operator of psi up and psi down is equal to 3. That's a pretty trivial statement. But if our two particles interact through a infinite scattering length interaction or unitary interaction, then when we put two particles in the ground state, they attract each other and form a new state, interacting state with wave functions, which can be written down exactly to be a Gaussian divided by x minus y. And the energy of this state is equal to 2 times h bar omega. And so for unitary fermions, the ground state energy of two particles in harmonic potential is 2 in the unit of h bar omega, and that corresponds. So this energy corresponds to the dimension of the operator equal to 2. So that allows one to read out the dimensions of the operator in the conformal field, non-relativistic conformal field theory describing unitary fermions by looking at the energy of state of n particle in harmonic potential, something that has been computed in Monte Carlo simulation and other methods. And one see the following. For two particles, the dimension is rather simple, 2. But when we put 3 particles in a harmonic potential, the quantum mechanical problem becomes rather non-trivial, but can still be solved basically exactly. And one find that the dimension of certain operator in conformal field theory, which in free field theory would have the same quantum number as this operator, but now the dimension of this operator becomes some irrational number, solution to certain trigonometric equations. The dimension of the operator is reduced compared to the dimension in free field theory to certain value. For 4 particles, the problem can only be solved numerically, and the dimension of the operator that consists of 4 psi would be equal to 5 to 5.1, which is the energy of 4 unitary fermions, 2 spin up and 2 spin down in a harmonic potential with frequency oscillator frequency 1. So this statement is useful because it right away tells us about the dimension of certain operators in non-relativistic conformal field theory. So one way this notion, this knowledge of operator that I mentioned is useful is in what we, Hans Hammer and I, call unnuclear physics in analogy with Georgi's notions of unparticle physics. So we imagine the following: we make the unnuclear physics is possible in nature due to the fact that neutrons have anomalously large scattering length. We mentioned that it's about -20, or precisely -19 Fermi, which is much larger than, say, the scattering length, the effective range of the interaction, which is only about 2.8 Fermi. So in a rather wide range of energy corresponding to these 2 length scale, the neutrons behave as fermion at unitarity. So let's consider the following situation. Let's consider some nuclear reactions with emissions of neutrons in the in the final state. So these are just some of these reactions. If we have such a reactions, then and if the neutron in the final state have have an energy that is small in their own center of mass dash frame, then this final state neutron can be considered as forming a rather fuzzy object, which we call unnuclear, which is described by a field in a non-relativistic conformal field theory. The regime of validity of this picture is when the kinetic energy of the neutrons is between 1 over a square, which is about 0.1 MeV, and 1 over R0 square. R0 is the effective range of the interaction, which is about a few MeV. So we have a rather large range of energy in which the neutrons interact with each other as if they are fermions at unitarity. So let's consider this picture more. We have suppose we have a reaction where we bring two particles together, particle A1 and a particle A2. So they interact and then emit a particle B and a few neutrons. So in this picture, 3 neutrons. But if these 3 neutrons have low relative energy with respect to each other, basically they travel together, and one can interpret this process as happening in 2 steps. The first step is the step in which we have A1 and A2 coming together, emitting B and some object that we call an unparticle U. And this unparticle then decays into 3 neutrons. The reason why this picture is this picture is valid only when the particle ends are emitted almost collinearly, moving in the same direction, almost with the same velocity. Because then they would split from each other at a much larger distance from the primary reaction than the size of the primary reaction, size of the region where the primary reaction happens. So this can be like 20 Fermi, when the size of the primary reaction would be a few Fermi. If that is the case, then we expect the differential cross section, which here is written as d sigma over dE. E can be thought of as the energy, say, of the B particle, to be a product of 2 parts. The first part is the part that comes from the primary reaction, and this is the decay of the unparticle U to neutrons, 3 neutrons in this case, for example. So here I have the primary reaction rate to contains a factor which is a kinematic factor depending on the energy of the B. But what is important is that it does not depend on the relative energy between the neutron if the neutrons have all emitted in the same direction. So doing a little bit more algebra, we can show the following fact, that if we look at this rate of these reactions, then it has the following properties. So let me draw a picture here. So let me draw a picture here. If I plot the differential cross section as the energy of the B particle, the final particle, it will have some form, some curve, which goes to 0 because the B particle, the spectrum of B particle will have a cutoff, some energy E0, which determined by the energy of the incoming particles, the Q value of the reaction, etc. But this E0 is some values that one can fix. And the behavior of the reaction near this endpoint is given by a simple formula, a power law dependence, where this delta is the dimension of the unparticle U. That is the operator that corresponds to 3 neutron, 2 neutron, 3 neutron, 4 neutron, etc. So this behavior comes from the imaginary part of the propagator of U, or in other words, the decay rate of this unparticle into 3 or 4 or 2 of the neutrons. This statement can be then applied to our reactions with 2 or 3 or 4 particles, because we know the dimension of the operator. So let's recall d sigma over dE is equal E0 minus E. So E is the energy of the particle B delta minus 5/2. Okay, so when we apply this to, say, a reaction with 2 neutrons in the final state, delta for 2 neutrons here is equal to, and so we find that the reaction with the emission of 2 neutrons should have a rate that diverges near the endpoint. It diverges like a square root of E minus E0 minus E, and this behavior would then have to terminate very close to the endpoint, because the neutrons are not really do not have real infinite scattering length, but only finite but large scattering length. So this behavior, 1 over square root of E0 minus E, has been known for a long time. Already in the 1950s, Migdal and Watson derived this behavior. But for 3 or 4 particles, now we can make a prediction that are new. The behavior of a reaction with emission of 3 particles would have to be cut off at near the endpoint by power 1.77 for 4 particles, e to the power 2.5, 2.4. The regime of validity is between when the relative energy between these neutrons is about 0.1 to 5 MeV. Let us now try to compare this prediction to experiment. So Hans and I were not able to find data that are precise enough near the endpoint to compare with our prediction, but we found the more theoretical calculation using microscopic models of nuclei and reaction, and we were able to confirm this prediction for certain reactions. So these reactions that we have here, I forgot to put the reference, but this is a reaction where we have a pionic. Basically it's a decay of a pionic atoms consisting of a pion pi minus rotating around the triton, and when the pion pi minus is absorbed by the triton, some fraction of this reaction goes into emission of photons and 3 neutrons. So now we can by measuring the energy of the gamma, we can determine the energy of the 3 neutrons in its center of mass frame. And here we plot the result of certain model calculations, microscopic but realistic calculation of these reactions. This is the rate as a function of the energy of the 3 neutron in its common center of mass frame. So we see this point, the point is this point here. Just note this point. These points are the result of the calculations and seems to fit the simplest power law very well. These points correspond to the result of the same calculation without final state interaction between the neutrons, and it seems to fit the curve drawn for non-interacting particle with the power 3 instead of 1.77. The same comparison can be done for the similar reaction with the muon. There is the pion pi minus replaced by the muon, and emission of photon is replaced by nu mu. We also see this several points seems to fit quite well with the simplest power law behavior predicted by non-relativistic conformal field theory. And so this indicates that that our prediction is isn't just some curious theoretical facts about unrealistic field theory, but it seems to be approximately satisfied in real nuclear reaction. Okay, let me tell you one thing. Another application of non-relativistic conformal field theory is that we can predict the width of decays of n particles that form a resonance with small energy E. So imagine that we have, so the problem is the following. Imagine that we have a certain number of particles, say 4 particles, with some interaction between them that we don't know. But we can imagine that these 4 particles with some interaction between them is fine-tuned so that there is almost a bound state of these 4 particles. Almost a bound state in the sense that if the interaction is just slightly more attractive, we would have a bound state, but they are just not enough to make a bound state. So in this case, we can show that if the number of these particles is larger than 2, then we have a resonance. N is larger than 2 or 3 and higher. We have a resonance with if the energy of when the energy of this resonance is small, the width of the resonance is narrow, and the width of resonance is a function of E that goes like a power law of E when E goes to 0. So in particular, we can apply this formula to hypothetical objects called the tetraneutrons, which most people don't believe to exist, but there are some experimental measurements that seems to point to a possible existence of resonance coming that formed by 4 neutrons. So if you have 4 neutrons and for some reason the nuclear forces is such that this object is almost bound, then we know the width of this object would change, would behave as a function of energy. If we manage to change the energy of that object by changing the nuclear forces, the dependence of the width on the energy should be e to the power of 2/5, where this power again is the same delta minus pi-half, with the delta is the dimension of the operator that correspond to this object. Okay, so let me conclude and mention what we have managed to do. We have reviewed the notion of non-relativistic conformal field theory, and the most important fact about non-relativistic conformal field theory is that we have their objects that are not particles but can be classified by the dimension delta. One of the examples of these non-relativistic conformal field theories is fermions at unitarity, and this theory is approximately realized by neutrons, and it leads to unnuclear or power law behavior with non-trivial power in the differential cross-section near threshold of production of neutrons. And this behavior also can be seen in the decay of multi-particle resonances with with energy near threshold, resonances with very low energy. And there are also possible extension to other systems like the X mesons in hadronic physics. So thank you very much for the attention.
Well, thank you so much for the beautiful talk. So we already have a few questions in the chat, and maybe we start with those. So just unmute yourself and ask your question. So why don't we start with Dong Bei?
Hi, Dan. Thanks very much for your nice talk. So my question is, what kind of physical observables can we assign to unnucleus? Can we talk about its mass, spin, and size just like the ordinary nucleus? So how can we imagine unnucleus?
So in the case of two neutrons, it's rather easy to imagine such a situation. You have two neutrons with spin up and spin down, basically as a S-wave object that would be bound if the attraction between these two neutrons are just slightly more attractive. In the real world, they do not form a bound state, but we can imagine them to be some object with spin zero, angular momentum 0, and the mass is equal to 2 mass of the neutrons. So for this object, for example, that I wrote here, the 3 particles, so you can look at the operator and say this operator has spin 1/2, angular momentum 1, and the in this approximation there is no spin orbit coupling, so it's both can classify this object by both by spin and L, and the mass of this object is 3 times the mass of the neutron. For example, for this object we have mass 4, mass of the neutrons, and spin and angular momentum both equal to 0 for S-wave. So and parity, you can also define parity of this object as well. So these have the same type of quantum number, except for the binding energy. It doesn't have the binding energy. It's all the quantum numbers of a bound state.
Thank you. So can we move on to Feng Li?
Yes. Hi. So in the end of your talk, you mentioned that this unnuclear scenario can be used to evaluate the decay weights of some weakly bounded systems. And I also heard from my friend that for a weakly bounded system, they have some states called Efimov states, which also has a feature like scaling invariance. So I just wonder, is there any relation between these two scenarios?
Yeah, let me first maybe make a correction. These are not weakly bound system. This is weak. You can think about that. It's weakly unbound system. The statement that I made here refers to states that are not bound with energy E that is positive, so it can decay. So, but the state would have a very narrow width. So that the connection to Efimov's effect is it's rather non-trivial. When we have a system, non-relativistic system that realizes the Efimov effect, the scale invariant is no longer unbroken. The scale invariant is broken down to a discrete scale invariance, and the machinery of conformal field theory becomes more complicated, and it's I think one still need to understand the consequence of this Efimov effect on, say, the whole kind of physics that I'm trying to the results that we have been able to derive here.
Okay. Yeah, in the simple system that exhibits an Efimov effect is 3 species or 4 species, so you don't see it in just neutrons. The neutrons don't have an Efimov state.
But say helium-4 atoms, which are bosonic,
bosons, indeed.
Efimov effect, and this this is still, I think it's a interesting question of what is the say behavior of reaction that have a few helium-4 atoms emitted in the final state.
Oh yeah, good
We are
point.
working on this problem.
Okay, so Uli.
Yeah, I wanted, just for curiosity, you mentioned that for the case of 2 helium-3 merging into an alpha plus 2 neutrons, there is a 1 over square root singularity near the kinematic limit, and that it was found before by Zeldovich and others. How did they derive it, and how is that related to the work that you have presented here?
Yeah, this was done by Watson, Migdal,
Migdal,
and Watson, I think, in very early in 1950s. I don't remember how. I think Migdal. I looked at Migdal's both papers. Migdal's paper is very clear, but I already forgot how he derived it. Basically, it's a final state interaction between just 2 particles. So I think it's rather yeah. I can't. Yeah, I don't remember. Sorry.
So this agreement could be accidental?
No, there is no disagreement. This is agreement.
No. Yeah, but the agreement could be accidental. Or
With what he did?
Agreement cannot be accidental. The agreement cannot be accidental because we are looking at the same quantity with 2 different methods and just normal quantum mechanics rule of scattering theory should reproduce the prediction based on more general nonrelativistic conformal symmetry. So for 2 particles, the result must be the same.
Yeah. So if you put in the assumptions that give you large scattering length and short range potential, right?
Yeah. Actually, they did more than just derive the 1 over square root. One can actually go all the way to the threshold. So the behavior is something like square root of E0 minus E divided by like E0 minus E plus 1 over A or something. I'm 1 over A squared. Some formula that in the limit when A goes to infinity would be 1 over square root, but they can in this particular case one can actually go all the way to the threshold. In the case of 3 and 4 neutrons, we still don't have a similar formula that would be valid not only in this regime between 0.1 MeV and 5 MeV, but also below 0.1. That I think that is possible to derive.
Thank you.
Can I actually quickly ask about the tetraneutron? So what is the logic here? So if I had purely resonant interactions, then obviously the 4-particle green function would be completely smooth. So now I imagine that there's some other interaction that makes it resonant.
We can always fixing the 2-particle interactions does not preclude existence. So even when we have in the 2-body system doesn't have a bound state or resonance, we still can have a bound state of many particle. One example. Let's consider an example. So helium-3 atoms is such a system. They are rather far away from unitarity. 2 of these particles do not form any bound state, and 3, but 40 of the atoms would form a droplet, would form a bound state.
Mm-hmm.
And so one can ask here, so there is some non-universal physics could be attributed, for example, in the case of neutron, to 3-body interaction or 4-body interaction. The simplest thing one can imagine is that imagine that four neutrons with some strong 4-body interaction.
Okay.
Make it into a bound state.
So that's then somehow technically irrelevant at large distances, but it does make the resonance.
Yeah, it could make a resonance. The thing that it's not clear whether one can make a tetraneutron without destroying all the other things in nuclear physics. Yeah, that's what people are confused about.
So we have a couple of raised hands as well. So the first one is Nushu.
Yeah, thank you for the nice talk. I have two questions. First one is there is a nucleus called hypernucleus, hypertriton.
Yeah.
I guess you know the binding energy is less than 0.1 MeV.
Mm-hmm.
Yeah. How can we tell whether it's belongs to this your category class of unparticle, or it is a particle? We know.
Yeah.
Yes.
But it's almost an unparticle. But it's the following. Yeah.
Okay. Almost an unparticle.
Yeah. Let me correct that. There are a few of these interesting states, which one of these is what you mentioned, the lambda PN.
That's right.
So PN form a bound state, we know,
Yes,
but it's
yes.
rather weak bound state, only 2 MeV binding energy. And this
Correct.
whole thing has a binding energy that is very low, like 0 point something MeV.
Okay.
So this is one state. Another also interesting situation is the 2 neutron halo nuclei. One example is alpha 2 neutrons. So helium-6. Helium-6 is the following system. We have 2 neutrons, which is this can be now thought of as an unnucleus, 2 neutron unnucleus, and then they are bound to an alpha particle, and the binding energy of this one is less than 1. It's about 1 MeV. And there are more. Another example, maybe most extreme, is carbon-22. Carbon-22 also is nucleus, but with the same structure, carbon-20, but the binding energy can be, as people don't know, but can be less than 0.2 MeV. And so this seems so Masaru Hongo and I wrote an article recently when we used this picture of this object as a bound state of basically it's a bound state of a particle and unnucleus bound state, the core and the nucleus of 2 neutrons. And so now that this picture is pretty useful to construct the theory, effective field theory of this object. So the 3-body object is not an unparticle, but it's a bound state of a particle and a non-particle. So now that in this case is useful.
Okay. Thank you. Yeah. The other question is, I believe at the beginning of your talk you mentioned that this theory you are developing will be very useful for study the phase transition. But you did not really mention any of that. Can you make a comment on that? How to connect these two? We are looking for example, phase transition, critical points, things like that.
Yeah, that was what was useful with relativistic conformal symmetry. So relativistic conformal symmetry is a symmetry of say ferromagnet to anti-ferromagnet to magnetic to paramagnet phase transition. Non-relativistic conformal symmetry doesn't seem to have similar application in the physics of phase transition, although maybe we just don't know. But I'm not aware of any example where the Schrödinger symmetry is realized in phase transition. So that's all relativistic. That is slide.
All right. Again, thank you.
Thank you.
So Chun Wang.
Yes, thank you for a very beautiful talk. So my question is about the the unparticle is the unparticle made of only the identical fermions, like for example, if you have a number of bosons, so can they form unparticle?
Well, if you have two bosons, even two different bosons, but with large scattering length between themselves, positive, then this notion of unparticle would still be useful. Would still apply.
So it's only it's also valid for bosons, right?
Two
Even
bosons.
even the boson not the same. For example, P and is an alpha particle, and another is some kind of helium-4. So
Yeah, I'm not
they
sure.
have to be the identical particles.
They don't have to be identical particles. They can be two different particles. In the case of fermion, for example, basically you have spin up fermion and spin down fermion. In principle, they can have different masses, like in ultracold atoms. Sometimes they tune the scattering length between two different atoms.
So the interaction range should be very small, while the scattering length must be very large, right?
Yes, yes. But the particle can be different particles.
I see. Thank you.
You're welcome.
Zheng Yang.
Dan, thank you for this very insightful talk. So you mentioned the tetranucleon neutron in the end. You have a prediction on the decay with right. So but so there's a Nature article recently, right? They measured from June this year.
Mm-hmm.
So they show the resonance peak. So I wonder if this actually describe that.
It's hard to fit one point to a curve. So basically, they say they observe some object with a certain energy and a certain width. I forget what it is. Maybe 2 MeV. This is maybe 1.
Yeah.
So
there is a distribution, right? I mean, very large error bar.
Yeah, but it all corresponds to one theory, one system with imagine. So I'm not sure. But suppose that the result is correct, then we have in the 4 neutron system certain bound state and certain energy. Our prediction cannot be compared to that because we don't have the numerical coefficient in front. We have only the behavior. So our prediction basically has to be compared with certain model calculation in which one can verify this behavior by changing, say, some parameter in the potential and draw a curve that change how the energy of how the gamma, how the width depends on the energy. So we cannot right now directly compare our calculation with what they have.
Thank you.
Okay, maybe one more question, Yin.
Okay, yeah, thank you so much. And so I want to ask this. So suppose we are not talking about the Schrödinger equation. We are considering the linearized hydrodynamic equation for conserved density. So this is a usual linear diffusive equation. It seems to me it also exhibits the Schrödinger symmetry. So if so, my question is, what happens if we add nonlinear terms? Can we fine-tuning the nonlinear term in hydro to preserve the Schrödinger equation for the diffusive dynamics? Can we actually apply this NRCFT machinery in this context?
I haven't thought about it. It's a very interesting question. I'm not sure I can say right away. There is certain factor of I. So the Schrödinger equation has an I compared to the diffusion equation, and one has to be careful whether there is extension, is a version of the proper conformal transformation that keep the form of the diffusion equations. Yeah, so it's it's interesting question, but I can't answer right away. It would be interesting. It would be very interesting if there is a enhanced symmetry of the some nonlinear diffusion equation.
Thank you.
Thank you.
Okie dokie. Well, thank you so much. It's what, 10:15 at the East Coast. I think it's a good time to thank Son for the talk. Thank everybody for attending. Beautiful questions. Are there any announcements by the organizers?
No, but thank you.
We also thank you, Thomas. Yes.
Thank you.
So then I see everybody again next week.
Okay.
Yeah.
Very
Thank
good.
you.
Well, thank you very much.
Thank you.
Thank you. Thank you.
Bye.
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 So, who is next week?
John Capusta will talk about the phase diagram.
You had
you.
130 participants at the peak time.
Thank you. Okay, bye-bye.
Bye.
Bye.
Thank you.